in the spirit of a debate, like a classic debate, we're going to start with a quick poll. So let me start by asking this. Here, this is how it's going to go. First of all, I want to say, I don't know whose idea it was to co-locate ICRA with the Momo Fest, but it was brilliant, and I think we should do that every year. Yay! Okay, so here's your panelists. I don't need to introduce them. You know them all. They're really amazing, and they're really volunteered. Now, by the way, I want to mention, when they take on their positions, they're going to be championing an argument that they're assigned to, which they may or may not agree with themselves. So don't hold anything against them if they say something offensive or really rude or something you really violently disagree with, okay? Just bear with the process, okay? That's their job, is to be extreme. So this is the million-dollar question today. It's what we've been talking about over the last week, and it's an ongoing question. It's not the million-dollar question, it's actually the $50 trillion question. Okay, what's happening out there? And everybody in the world is convinced that robotics is about to tip, and we're going to have humanoids everywhere. And so the question could be also phrased as, when is the ChatGPT moment for robotics, right? This sudden transition that's going to turn us into everything that's going to start working. AI, the Turing test is going to be solved. When will that happen for robotics? So people saying, listen, large language has solved vision. It's solved language. Therefore, large data will solve robotics. Now, that's the question we're trying to debate here. And that many people have presented their work over the last few days, comparing. I've seen a lot of papers on model-free policies and a lot of papers on model-based algorithms. Very few that sort of combine the two, although there's some of those. But what we're going to do now is take the extreme position that it's either one or the other. Okay, so large data will solve vision, large data will solve language. Therefore, large data will solve robotics. So how many believe this is true? Raise your hands. Hold them up for a second. Don't be shy. Okay, good. Okay. How many believe, okay, I'm just gauging this visually. How many believe this is false? Oh, okay. All right. All right. The crowd has spoken. All right. So when is this going to happen? All right. No. All right, so here we go. We're going to start out, we're going to alternate sides. And first, Animesh is going to come up, and he's going to represent the true side, that data will solve robotics and automation. Then we're going to switch over to Aud, and back and forth like that. They're each going to have 3 minutes to present their positions. Animesh, please join us.
So thank you for inviting me, and I am solving or helping out the team data. Okay, let's start. The first problem I would like to show is we have been at it for a while. This is a video from 1968. This is the first robot that was built. Some of you may guess. Some of you may be old enough to know the robot. For most people, probably you were not born before that. The robot is Unimate. And our aspiration used to be always the same. Solve home robotics. The robot used to be pretty big. And see what the lady is doing, right? 50 years, cut to this. This is, I think, a year before from what we have. The kitchens look better. The robots don't look much better, right? So something's got to give. We have been at it with whatever sort of the solution, the structure idea, priors, inductive biases, what have you. It's just not worked, right? It turns out there is evidence, technical evidence, which says too much structure actually does not help. You can either build too much structure such that you cannot even represent the optimal solution, or you may build it such that the optimal solution is representable but not findable. So lesson one is we need to think about the other side of the coin, which is data. But thinking about data is not that simple. It's not like a naive thing to think scaling data. It's really we need to think about science of scaling. So it is a scientific problem. It's just that we have to think about it scientifically. Now, how to scale? One way to think about this is a very robotics idea, is think about the what problem. So you are thinking really solving the high-level problem of reasoning and common sense. And what you're really doing is, at a high level, building a foundation model that can generate references. And these references can then be tracked. This thing is something that we know from controls. You're basically doing reference tracking controllers. This can be closed loop. They can be reactive system 1 or deliberative system 2. But effectively, what it allows us to do is to ship off the hard problem of specifying common sense or specifying problems which are ambiguous and robustness to data. Data really helps with unlocking complex problem solving beyond what we can do with manual systems. And it effectively results in some sort of flywheel effect. The more robots you deploy, the more data you get, and then everything gets better. Part 2 of the question was, is handbook of robotics obsolete? Before we say it's obsolete, let's think about what is it. Most of you probably haven't seen it. It's this sort of Bible, or like 17 Bibles, actually. It has 80 plus chapters, 7 sections, right? This is only the last page of the contents, actually, just to show you that it actually has 80 chapters. This is the latest version. We cannot solve, robotics is a community of communities, and we have not figured out how to actually put everyone together. For the first time in many years, data provides a solution to this. Data-driven approaches effectively unify all of our methods. The problems are different, but we are basically building a common foundational base. So lesson number 3 is data really leads to a unifying perspective to all of the community, which is actually, if nothing else, that itself would be a useful thing to do, right? And then finally, I argue that robotics is not very different from all other complex things we work on, right? You use phones, computers. They are complex things. They are not a single software or a single hardware. It's what you'd call the stack. Start from drivers, modular OS, and then applications. Robotics, why should it be different? This is the next generation of computing. And if it is the next generation of computing, you can imagine that there is a low-level hardware-specific stuff, there is platform-agnostic OS, and then there's some sort of mechanism to write apps. And this will be the abstraction that we will build for the next generation of computing. It doesn't matter what robot are we doing this for. And that will also be requiring data-driven methods. All of these layers are effectively AI models. So the last lesson here basically is that we don't want data first to equate to lack of modularity. Data-driven methods does not mean that modularity goes away. And then finally, I do want to point out, a lot of people did say, oh, but supervision is not scaling or robustness or generalization. But that doesn't mean it has to be supervised. I think I like to quote Alyosha, the revolution will not be supervised. So teleoperation may not be the answer, but data will definitely be. That would be my time. Thanks a lot.
We can pull up Alan's talk.
Yes, I think.
All right, that was fantastic, Animesh. I think you gave Osama a heart attack there, but he's still okay. Okay, Aud, you're up next. You're going to take the other side. Okay, yes.
Oh,
All right.
okay.
Aud BR.
All right, okay. Where is it?
Yeah.
Oh, that's this one. No. Not that one. Okay. Which one? I'm sorry. All right, so I hate to break this news to you, but Animesh is all wrong. They're all wrong. We're correct. And because the truth is that our goal in robotics and in science in general is to fulfill humanity's quest towards understanding. I take here my physics hat. Look at many of the core science, cosmology. Sure, there is data, observation of the stars, observation of the planet. But it's not because you're observing the planet that you build understanding. It's not the data itself. It's what you make out of it, the physics law that explains it. It is the same for biology. Yes, there was the Golgi stain in 1873. It was the first way to see inside the brain. And then there were many other techniques to highlight neurons. But it wasn't just looking at them that made it what we understand from neuroscience. It was the development of biophysics model. It started with Hebbian learning, just the ability to connect two neurons together and to learn from that, to make sense of the data. Actually, a neuron makes sense of the data when they connect to one another, not just because they observe the data. Now, today, we are in a different world. We are creating. We create neurons, artificial one. I want to believe that we create to understand, not to observe. Of course, we need data to help us verify that the model we build are correct, but our core goal is to understand. We go one step further, we create humanoid robot or robot that look a little bit like us. Why do we do that? Because we want to better understand ourselves. And to understand, it's not just embedding data, embedding modeling, it's understanding to be able to gain control. We've done that with physics. We've been able to fly rockets onto the moon. We've been able to do many different things with biophysics and neuroscience because we understand the process. In robotics, to understand is to gain control. This is ZMP control. This is stability for you. Of course, it needs a little bit of data to be able to tune it for the different dynamics of the robot. But at core, it's the physics behind that. There is a process to get to have more data and more control. It's to learn from it, of course, so you can fail and relearn, etc. But I want to close by saying data is like having books in your library that you never open. Data without models are just data, and models is what convey understanding. So we are right. Thank you.
Okay, that was excellent. Thank you, Ad. And appeal to physics and human understanding. And now we're going to hear from the other side. Daniela Roos.
Yeah. Did you notice the cables holding the robot that was balancing? Can't do that with algorithms. In fact, no amount of algorithmic innovation can substitute for data in robotics. Data is the foundation upon which we can build complex, generalizable, adaptable, resilient systems. So, we can model simple tasks from first principles. We can model grasping a known object. We can model balancing a rigid body. We can model navigating a predefined path. Because the physics is tractable and the assumptions are clean. But the real-world robotics is not that clean. If we want robots in the real world, if we want robots to really make a difference, then we need to think about how the grasping of a familiar object becomes picking and placing in, let's say, a very cluttered drawer. You can't do that from first principles. Similarly, navigating along a predefined path in the physical world means navigating in the social setting where, just imagine a bunch of humanoid robots trying to find their ways to empty chairs. It's inconceivable, right? Those are two complex mechanisms. So we cannot capture the complexity of the physical world from first principles. From first principles, we can really only model specific, very constrained scenarios, but we cannot generalize to other environments. We cannot support adaptation. And data provides the experiences that lead us to policies that support adaptation, that support the complex behavior in complex environments. Data also enables less mechanistic motion, so let's be serious. All the robots we model from first principles are very mechanistic. But if we want robots in human-centered societies, then those robots have to be much smoother, much more adaptive to how humans behave. And so, when I talk about that, I'm not talking about some distant imaginary future. We can actually do it. Data is already making a difference right now. And data is making a difference when it's coupled with the new kind of machine learning models called state space models that embed physics, that can do spatio-temporal correlations, that can do the kinds of things that we need for physical AI. And I just want to give you an example to show you how easy it is to go from data to smooth, complex operations. So this is an example of a task in our lab where we instrumented a human with muscle sensors and also with tactile sensors and the pose tracking. And we collected a lot of data about how humans do complicated tasks in the kitchen. And then we use this data to learn a policy that teaches robots how they should do the same complex task that cannot be modeled from first principles in a way that is smooth, that's human-like. And so the end result is machines that move with grace and agility, as well as adapt and learn and generalize and can do complex tasks. In other words, real-world physical robotics. Thank you.
Fantastic. Thank you for sticking to your point of view, your assigned point of view, and also for sticking to the time commitment. And Leslie, you're up next.
I just want to make sure that your thing is up. Yes.
Okay. Will data solve robotics and automation? No. Data is not all you need. Okay, so a lot of us want to have general purpose robots. I'm going to think about general purpose robots, not special ones. Special ones are good and important, but that's not what I'm talking about. So where do we get generality? Here's some data. Where do we get generality? Well, I don't know. If you fit a complicated model to a few data points, you might get something like that. So I don't know, where does generality come from? The answer could be, well, generality comes from data. Like if we just fill the space with data, then we'll get generality. But maybe not. So where else could data generality come from? Data generality can come from priors, right? Priors, okay. So, here's one way to get generality, really a shit ton of data. That's one way to get generality. Or you could know something about your world. So, is it data and a little prior? That's the bitter lesson. Or is it like prior and a little data? I don't know. Okay, so where do we get priors? What do we know about the world? I don't know about you, but I believe that I exist in the physical world in 3 dimensions. Maybe you don't, but I do. So, there's the real world. There's the geometry of three space. Causality in the flow of time, physics, folk psychology. I believe that you're an intelligent, sentient being. Maybe you don't believe that about me, but I don't know. There's structure of information, sparsity, locality, hierarchy, abstraction. These are important principles that we can apply to learn more efficiently. We can use algorithms as priors. Algorithms are general purpose machines for converting representations from one form to another. Search methods are such algorithms. Dynamic programming is such algorithms. Inference methods are those kinds of algorithms. You can build those in as priors, and they give you an enormous amount of leverage. So I think amortized work that we put in to build priors will be cheaper, will pay off more than just blind data collection. And if we do that, we'll build robots that are easier to verify and more human-like. So will data solve robotics and automation? No.
Okay. We got a big heavy hitter coming in here to take the interesting position that data is all you need from one of our world experts. Go ahead. Russ Tedrick.
There you go.
Okay. All right, this is going to be fun. Yep.
Because this is not a presentation, you probably have to do something here.
That's fine.
No. Oh. Wait, it needs to show up there, right? Somewhere.
Yeah.
I don't know how to do this. Yes. Okay.
Thank you, sir. Okay, let's do this. So, Ode, I think that if data without models is just data, books on the library shelf that you don't read, I don't know, GPT feels a lot more than that to me, right? I think we have to admit that priors, these big models are learning the priors. And actually, Leslie, I think my priors are better than your priors. So let's do this thing. Okay, so I'm on team true today. Let's have it. Why am I on team true, right? So there's exactly one thing that I felt like I could never do with my models, right? And that is to program common sense. Leslie's called it background utility. There's a bunch of different ways to talk about it. But I don't know another way than through data to program common sense into my robots. For perception, language, video, maybe it's inevitable that robots, I actually do believe that. And I think most of us would agree that for open world generalization, like pick up the extinct animal, then that's okay, large data, that's going to help with problems like that. But what many of you who raised your hand incorrectly at the beginning might be underestimating is how important common sense is for low-level control. Really, I think so. So there's a lot of common sense down there at the feedback level. And as Exhibit A here, let me just show you one of the fun videos we made pretty recently at TRI. Okay, so simple robot, lots of data, but lots of pre-training data, and actually only a day's worth of training on this robot. So 300 or so demonstrations of this task as one end-to-end task on a pre-trained model that was trained on more than 500 skills, gets us to these really, really dexterous tasks with very subtle recovery kind of maneuvers that I think evoke common sense and transfer across tasks in ways that I just don't think you get without some of these really complicated sort of data-driven models. I'll fast forward a little bit if I can control that screen. Okay, but watch how some of these, look how accurately the knife is being held in the gripper. Not at all, right? Think about how long that sixth link is. If you've ever done sort of, your model-based control and thought about controlling an end effector that has this weird kinematics to do super accurate, flipping and stuff like that, that's extremely hard. That's only happening because the feedback control, low-level feedback control, is happening through the vision, and it's doing visual servoing and the like. Now watch that. The apple slid off. There's a beautiful little recovery. These are the kind of things that you just don't get. Or if you maybe raise your hand if you spent months programming a state machine for something like this. It's painful, right? I've done it, but we did this in a day with no new lines of code. It's great at the end. It actually will clean the knife and sheath the knife, put it back. It's pretty good. This last part, this is the hardest part. When it fails, it normally fails on this part. It puts the knife away. Right? You see enough of those day in and day out, and you start believing in data, okay? I would say even those of you that are doing mechanical design is about common sense. The reason it's been hard to automate is we don't know how to evaluate, close the feedback loop, but I think it's coming there too. Okay, is the handbook of robotics obsolete? Osama's looking down, so I'm good for a second here. I think many of the concepts in there are fundamental, but I think the algorithms need to adapt, really. Just an example, motion planning for a dexterous hand. We should not plan every time as if it's the first time we've ever solved the planning problem. That is so inefficient, and it makes the problem artificially hard. And for the first time, we don't have to do that. We can come with a tome of knowledge, of data that we've had from solving the problem before. And I think increasingly the algorithms that we will deploy on data will be data-driven. So my call to action here is, well, first of all, embracing data, which is my stance, does not mean know-nothingism. Okay? Absolutely, we need to believe in these things. You should read the Handbook of Robotics. You should study it. You should use those algorithms to probe this intelligence we're building, but then you should probably deploy the data-driven version, yeah? And, large models have changed everything, but it is a long journey, and I agree we need to understand it.
Okay, Russ, how many times did it work, the coring the apple thing? I know, I'm teasing you. All right, but not every time. But what I want to say is, good. I like the assertion. Your priors are better than Leslie's priors. We should get personal, and we will, by the way, in a rebuttal session where everybody gets a minute to come back. Frank Park.
All right. Yep. Thanks, Ken. So you heard some nice, eloquent intellectual arguments. I'm going to be much more down to earth and talk about some of the practical issues. So, I interpret this question as, are robot foundation models possible? So many of you have probably seen this article in ICRA Spectrum Robotics. Very nicely written article. Excellent points. RTX, I think I checked about last year, so maybe there are more, but right now it looks like there are, 22 embodiments, 500 so skills, 60. Tell me if you think we're close to where we need to be. All right, and everybody knows about this, right? Software that would work on any robot, eliminating the need to develop software for each specific task. That's the goal of a robot foundation model. So let's talk about what goes into a foundation model. So this is all obvious stuff, right? Massive computing. So I remember OpenAI had a data center in Iowa the size of a football field. The one they're building now this year is the size of the Empire State Building laid on its side. There are no more nuclear reactors that they can build next to, so gas turbine companies are doing really well selling gas turbines. And I heard well, of course, you have to be next to a river, because these things get very hot. Let's mention, there's a lot of, sort of stuff that goes in the foundation model besides just GPUs. I mean, you have to do data collection, monitoring, retraining, scheduling. There's a lot of infrastructure, very costly. You've seen articles like this, call it the end of the beginning of the AI boom, and you're reading about all these companies running out of money. This is not sustainable, obviously, right? How large does the foundation model need to be? All right, so this is a double descent phenomenon. Leslie showed the similar graph, right? Underfitting, overfitting. Machine learning, it's basically a function approximation, right? So we want to hit the optimum. So here's a graph of size. So the x-axis, think of as sort of the size of the model, data. Y-axis is performance, right? So there's sort of this optimal point between underfitting and overfitting. But as you keep going, as you keep increasing the model, throwing more data at it, it mysteriously gets better. And the point of this article is that nobody knows why this happens and where it happens. So this is a double descent phenomenon. I kind of inverted the graph, so it's double ascent. This is interesting. Nobody knows, right? Here's Moore's law, right? Every 2 years, performance doubles, price halves. The graph for AI models, it increases performance, cost increases with performance, probably even more than linearly. So this is a reality today. Let's talk about robot foundation models, all right? Text, language, vision, okay. Robots perform very diverse tasks. Embodiments are incredibly diverse. What's robot data? It's more than just motion, right? There are force sensing. There's also compliance. When we're doing manipulation tests, there's some compliance at the hands. There's also compliance internally at the joints. We can form open chains, closed chains. Where is all of that, right? You saw examples of this. I mean, come on, right? We can't be doing this. All right, so we'll use simulators. I know simulators are getting better, but for especially tasks involving contact, manipulation, they just don't work very well. And robots wear and tear. So these models have to be updated after some time. And I think I saw some Waymo cabs in Atlanta, right? I love this title, When Self-Driving Cars Don't Actually Drive Themselves, right? So there are people watching you in a control tower just to make sure that accidents don't happen, right? And robots, there are many situations where robots, you cannot have them fail, right? So you can't have control towers like this. Robots are much more complicated than cars, all right? So Tesla has had data accumulated, hundreds of thousands of vehicles, 10 years. They still can't. Level 5 is just around the corner. They've been saying that for the past 10 years. Okay. So, the right way to build a foundation model. I think, so this is, all right, sorry, okay. All right. Okay. Shift invariance, permutation variance. These are some of the, hopefully I'll talk about this later. But anyways, my point is, when you start putting all these inductive biases and the common sense that we know about into these models, it's no longer a foundation model. So, answer is no.
Okay. Daniela is chomping at the bit back here, but you have to wait, Daniela. You're going to get a turn. Don't worry. So Animesh is going to be first. So everyone's got 1 minute to basically push back on anything you've heard, and then we're going to take some questions from all of you. Okay.
I just wanted to go first because I want to say that our preeminent negative side ought to get more current with the state of the art. So they claim that, that data-driven computation is not causal. Well, there are plenty of papers that talk about causality in robotics. They claim that we need these huge foundational models in order to solve data tasks that are rooted in the physical world. Well, there are plenty of papers that talk about non-transformer style models that can actually run on device, that can run on the robot, that can run even on your phones and on laptops and on any other edge devices. They claim that the carbon footprint of foundational models is too large, but not the physical AI models that are not transformer-based. And so, let me suggest that they read more papers. Thank you.
Okay, Animesh, you're up next. No, you're right. Out. Let's bring you up next to position. And I love Daniela because she didn't get where she got to without being really tough and taking the situation into her own hands when she needs to. So I love that about you. All right, out.
So not only do we not need more data, but we don't need more papers. No, I mean, seriously, that reminds me a little bit of some of my students who come and tell me, oh, I need more exercise to better understand the theory. And then they go like, I need more example of what the exam will look like to be able to pass it. I need more example of this, more example of that. The problem is not there. The problem is the understanding. It's the model. They really didn't get it, didn't they?
I think this is a story we have heard a lot. The story goes always the same way, where we know a lot, we should code it up, maybe we know about 3D, we know about something, and then that should go in the deep learning model. And then eventually what happens is, in a year or so, the data scales by 10x, and then suddenly everything, voila. So this happens over and over again, the story that the model cannot do X this year, or deep learning is hitting a wall. And the answer usually is you just need a little more data. So yeah, so you need to look at, because AI moves a little too fast, so 2024 articles are ancient history we should be looking at last week.
Okay. So a lot of folks like to talk about the data flywheel. And first of all, a flywheel is a battery for angular momentum, and it's a bad simile. But anyway, I think that there's a really important data cycle which involves understanding. If you arrive at a problem with already a pretty good understanding of what's going on and you see one demonstration, you can learn a ton from it, and that helps you learn more. So I think we need a virtuous loop involving priors, where you have a strong prior, you see some data, that improves your prior, you see a little more data, your prior gets better, and that's the loop that's going to win intelligence for robots.
I'm pretty sure Leslie just came half over to team data. And I'm pretty sure Ode's trying to distract you with theory of science and paper publication, but those are not the topics for today. Don't let her distract you. I think the real thing here is that data is the path to better priors, I think. The problem with our priors, well, first of all, 3D geometry. I think we're learning 3D geometry in these models. If it's so prevalent in the world, then it's probably one of the first things that these models pick up, right? Physics. I love physics dearly. Many of you know that, okay? But physics isn't enough, and it's too specific in some ways, and it's not enough in other ways. What I need is very contextual, task-relevant models. And the types of priors, we don't yet have the math to describe those. The way we get the math is from taking the data and then studying it.
I know that the Yes team really, they don't really believe what they're claiming. They're kind of with that stuff. But, so there's not much to rebut here, but I'll just, make that point again about, just building the right foundation model is not just throwing just data and just computing, but really building on the layers we know. We talked about priors, inductive biases. We have so many great sources of inspiration. Human motor control, physics, mechanics, obviously, geometry. These are the things that we need to use to build, the right models and on top of the right programming, motion description architectures. And when you're done with that, I would not call it a foundation model. So.
Okay, excellent. Okay, so I can see that there's a lot of opinions for being changed out there. But let's take some questions. So there's a microphone right here. So please come down if you would like to ask a question of the panelists at any point. I'll ask a couple of them while you're getting set up. So one is about the scale. We're talking about data in sort of an abstract way, and one of the things that's interesting to think about is how much data is in these large vision language models. So there was a nice post by Michael Black, who was at Physical Intelligence, and he basically made the equation of how you can transform the data in language models into time. Because basically, how long would it take you to read the amount of data, the amount of texts that are used? And it turned out that it was about 100,000 years of data in these large models. So, and Physical Intelligence, for example, I don't want to pick on them, but they announced recently their model, which was worked out to about 10,000 hours, which is approximately 1 year of data. So by that token, we are getting there, but we might need 100,000 years to get that equivalent amount of data, because we don't have it on the internet. So that's a vast, just keep in mind the vast size of it. Not to mention that the data for robotics might be more complex and nuanced than the data for language and vision. So I just want to put that into context. I'm happy to let any of the panelists respond to that. Just jump up to the, good. Come on, Russ.
I am so tired of this analogy between language and robotics. Language was designed by evolution and society to be easily decodable, to wear its compositional semantics on its sleeve. But robotics is not like that. The data that we have to learn from in robotics doesn't tell you how to decompose it like language does. So it's going to be way harder.
I think that's hubris. I think it's easy to say my domain's not susceptible to the scaling laws, but when it starts working, you got to revisit your basic assumptions. And how much data do we need? I think you'd be surprised how well you can go with modest amounts of data. We don't have to start from scratch. Doing dexterous manipulation is not like quoting Kant. It's you don't have to do that. GPT already did that. We're going to leverage those pre-trained models, and then just add a little bit more robot data.
So there are models and models. The transformer model does not have recurrences. It's a purely feed-forward model. It's a memorizing model. In the transformer model, you need a lot of data because the model itself is memory. But in state space models, where we have recurrences, where we can learn from the past, we end up with models that are much smaller, that can do spatio-temporal correlations, and that do not need so much data in order to train them about the physical world.
Great. Thank you. Thank you, Danielle. So we have I see the questions lining up. So go ahead and try to keep them short and sweet. Go ahead.
To the data side, how can I ever build enough trust to let that knife-wielding robot near my 18-month-old? And to the anti-data side, how much fluid dynamics does a bird know?
Okay, good. Yeah. But you can fight to get up on the podium too. So Russ, do you want to jump on that one?
So Jeff, one method for ensuring the trust of a data-driven solution is through combining machine learning with control theoretic solutions. So, for example, one solution we call barrier net adds a layer to the model. This layer represents the safety conditions for the application at hand, and then you have a guarantee in a control theoretic sense that the output of the model is safe.
Okay, good. Russ? Yeah.
So I wouldn't put your kid next to my knife-wielding robot anytime soon. Please don't. But if you need robots to wield knives, and it's the best approach. I remember talking to somebody who went the early ages of deep learning for vision, and they were doing guided missiles. And they said, I said, how could you possibly do that without verification? They said, it works so much better. How can we not? And I think that's what's happening here.
Excellent. Okay, because I think there's going to be, at one point, there's going to be a thing where, I remember someone did a razor cutting, shaving, and I think we should do a data-driven version of that. And Russ will step up and volunteer. We'll do a demo next year. Okay. Okay, next question.
To the data side, what do you think about using synthetic data to train real models? Because to me, I think it's using fake data to train real models, and that's a contradiction I can't wrap my head around.
I think a lot of the new models, even in perception, use purely synthetic data, and you can go surprisingly very far. I think Russ already said, surprising amount of complexity in synthetic data in the background and stuff is not something that you really need. If you're cutting watermelons, does it really matter what the background is? So you can really get very far with very good synthetic data, even if it will not be the last mile. So in that sense, actually, synthetic data is easier and cheaper to generate, and you can go very far before you need any real data, if at all.
Synthetic data is a model. Yes, synthetic data is a model. He got it right. Right. I just want to say, right, if you have a simulator, you have a model. And that RL algorithm is just a compiler.
And I'd like to go back to the fluid dynamics question. Yes, the bird has the fluid dynamics in its brain, but it's not written in mathematical equation. And in fact, what we are never discussing is the language of the model. How do we encode that? Is it in code? Is it in actual language, whatever the language is, or is it in mathematics? But yes, I stand that it has a model in its brain, whatever it looks like.
All right, great. Next question.
Right. Any comment on social justice aspect of it? Because, it is polluting, it consumes a lot of energy, resource. So even if data will solve robotics and automation, I don't believe so, but even if so, if it destroys humanity in long term, that's not a solution. So.
All right. Okay, good. So is it going to steal jobs, take over, and wipe out humanity? Does that matter?
To be clear, the question of the debate was, will it solve robotics? There was nothing about humanity remaining intact.
But I do want to say that the new models, the state-space models, are 1,000 times more energy efficient than the transformers for both training and inference. And the carbon footprint is nowhere near what we imagine by continuing to scale up the transformers.
So they'll take over the world more efficiently.
Okay, next question. Good.
Okay, so I like to widen it a bit. I actually think that everyone on the panel, and probably most of us here, agree much more than if we had brought in a panel that was half from the AI/ML conferences. And I'll just bring something up there that, of course, we all know these models, and I'm all for science like Odd, right? My background is physics. I use, projective geometry whenever I model, a vision task. But people in, mainline AI, they don't think about these models. In fact, there is something on Richard Sutton's. He says that modeling is pointless because computation is going to grow so much faster and be so much more impactful that modeling cannot catch up, right? And I was his housemate for a while, right? And there was really no conclusion in this debate. So how, and these are our peers, at least in a broad sense, right? So how do we talk with them and give our points, right? How would you formulate your points in the view of people who says, I will only input my high megapixel video, and I'm only going to output my robot actions, right? I don't want to have any model in there. What do we say to them? And can we agree with them?
Yeah, no, I wish Rich Sutton were here to speak up. We would have had him on the panel for sure. It is the bitter lesson, right? That is really what we're debating as well here, right? Because he's saying everything in his experience, has yielded to data in the long run. So Rich Sutton's arguments are kind of on the side of the data. So it's a good point. If you're his roommate, then we should get him here for next year. All right, thank you. Any other comments from the panelists on that point? About the general AI view, if you were at an AI conference or let's say NeurIPS, that it might be a very different kind of debate.
Okay, we're supposed to be bold, right?
Yes.
So we don't talk to them, we just let them fail, and then we continue our way.
Good. I'm glad to see we're getting the spirit here. All right, Leslie.
Okay. So I think the constructive answer is that we all have to build the thing, and we'll find out, right? We'll find out how many demonstrations is this much work of pre-programming worth, right? I mean, in the end, it's just it's not an ideological decision. It's an economic trade-off, and it'll come out in the wash. Eventually, one side will win. Maybe I know which side, but some side will win.
Okay, good. Next question.
Hi all. I want to have a question like for both the data team and also the anti-data team. It's like, so what do you guys all think about the intuitive physics, or what we call it? It's like a model, like for those model-based people. You can use the intuitive physics to try to do MTC, do model-based RL, or use the intuitive physics model to do anything, or even you can actually do VLA if it wants. But for the anti-data team, for the data team, so this kind of intuitive physics model is actually generalized. It can be generalized, and it's very general because it understands a very low-level intuitive physics, but it is actually constructed with data and all of other stuff. So it's kind of, you can also see it as part of the VLA model. So yeah, I want to hear about how you guys think of this idea.
Okay, good. Any responses to intuitive physics models? Animesh?
I think one thing, and this will also be a response to Odd's answer, we need to build functional systems first, and currently, as far as we know, to build scalable functional systems, data is the only solution we know. The other part we have tried for a very long time, and we don't have a scalable solution. That said, we can study it if it is probable and it's learning something, it's fine. It's very unlikely that you'll be able to get out the exact equations of physics as long as it's statistically similar. So I think intuitive physics is a very good idea as long as we don't try to sort of equate it to Newtonian physics or something.
Okay. Well, you're saying that the only way we can build scalable structural systems is with data? Did you just say that?
Currently, yes.
Okay, but that's going to be news to all the people who are exhibiting at Automate and all the big trade shows, okay? Because they haven't really, they have scalable systems out there that aren't using any data whatsoever. But I hear you. Okay, next question.
Yeah, so this will be quite high level, but what is solving robotics for you? Is this because I see the humanoid robots, for example, at ICRA, and I'm not sure, is this what we're after? What does it mean to you? I don't know if it's this high level to the point of being meaningless, but...
So slow, yeah. Okay, I use the word solve extremely carefully, and I was, in life, maybe not when I'm asked to be controversial. But no, I think that's really delicate. But for me, the end of this pipeline is theorems. Really. not like next year, but like, and those theorems though, do they start with Newtonian physics, or do they start with us understanding and thinking in new ways the open questions that have emerged by having very large parameter landscapes and data that feeds this, right? I think there's a whole bunch of new questions that will be required through the data path till I consider it solved. I'm just advocating that the solution takes a path through data.
Ooh, that's very interesting.
Good.
Okay.
I mean,
Go ahead.
this is a hobby horse of mine, actually, and I think it's really important, and I'm super happy about the question, because I think we all probably have a somewhat different definition of what it means to solve AI or robotics, and we have a particular part of that we care about. And the solutions are going to be different depending on the problem class that you're trying to solve. And it's actually harmful to the field to set up this opposition, because I actually think that the answers are completely different depending on whether you're trying to improve factory automation or send a planetary rover to a place we don't know very much about, or make something that can be a general purpose household, whatever. So we should define our problem and then have the fight.
I do want to respond to that. This is exactly what we thought in 2019. My problem is way too different, and then Transformers happened.
Yeah, it's a great question. Actually, I think it's interesting. I think Russ's answer has very much surprised me, because I didn't think of that. And really, when I was formulating this, is solve it in the sense of having the robots out there in the world working and all those things. That's what I thought about. But you're saying solve in the sense that we'll understand it ultimately, which is a really interesting twist on the debate question. Good. How many points? You get a couple points for that, for sure, definitely. Okay, next question.
Okay, so this speaks to Leslie's point about the data flywheel. I mean, clearly, black box models encode our understanding of the physical world. So isn't really the problem not whether data will solve robotics or not, but isn't it just that our black box models take too much data to understand the physical world, and we don't know what the hell they're doing?
Okay, so this is me and Ode together, right? I mean, I think, right, I don't know. I can't speak for the other model-based people, but I don't think any of us think that with an infinite amount of data we can learn anything. I think we probably all believe that. The question is, what's the trade-off between data and prior? That's all.
Yeah.
Yes.
Thank you very much. My question is about, a constatation is that robotics takes a very good thing from biology, from neural networks. So a lot of achievements in robotics, they are due to how we understand biology, brain, etc. How patterns can be formed in the brain. So actually, robotics also has to give like a feedback to understand biology, to give not advices, but how to understand how the brain works, how patterns in the connections of the brain are constructed. So this requires a use of data in order to make those patterns. So this is my constatation.
You triggered a reaction. Go.
But he's not done, so you're done?
Thank you. That's all, thank you.
Okay. Yeah, so definitely, robotics is to create and to test models and with new data and to verify our understanding of things. And to the previous question as to what does it mean that robotics is solved, I actually asked myself exactly that question when I received it from Ken. And I'm sorry, Ken, it doesn't mean anything. No, but really, it's a quest. It's a quest towards more understanding. So it's a long quest. We are never going to stop. We're going to continue understanding more about the difference between what is artificial, what is biological, what is life. Is it really the definition we have? There is no good definition of life. There is no good definition of death either, by the way. So yeah, this is a quest to go one step further. And every single step may allow us to build a better understanding of everything.
Okay, good. Good, Russ, go ahead. The brain.
Okay, yeah, so first of all, I think we have to acknowledge that the intelligences we're building right now are not do not have a parallel in the natural world. Like GPT is not a natural intelligence. But to twist your question a little bit, I actually think we need to start acting more like biologists, because we are building these things that we don't understand, and we have to be better at science than we have been traditionally in this community, I'd say, and probe and understand these big things that we're, like a scientist, like a pure scientist, right? So for sure. I agree with Ode's total mission. I'm just saying that we have to be willing. The path to getting to ultimate understanding of intelligence and control for robots might require us discarding the models we've been building for a while and thinking differently about the new tools.
Very good, very good. And Russ is, just so he has been really applying very solid statistical methods to experimentation, which I really appreciate. You've been really leading the effort in that way, and also working with Hadass on this. Next question.
My question is, if data cannot solve robotics, what else can? And who on this planet has the capability to hand code a system that solves robotics without data? Thank you.
Thank you. Thank you. Oh, no.
No, but the point is, data is needed, but it's insufficient on its own. The true thing that may help solve part of robotics is the model. Data, imagine you have data. If I give you the motion of one planet, you observe it. Then I give you 10 planets moving, 20 planets, 100 planets. Will that help you understand the motion of one planet? No, it's sufficient to see only one. So yes, you need to have the data to start with, but you need to build a model out of it. So what we are saying in the camp that is right is that model is what matters. And the data comes first, of course, but on its own, it's insufficient.
Good. Okay. Yes, and thank you for that. And I think we're seeing a little bit of a generational divide on this question, which is really interesting too. Okay. Thank you. Next question, and we're going to just take two more. Well, three more, and then we're gonna wrap up. Okay. So.
Hi. Well, speaking of generational divide, I spent the last 25 years of my career on the data side of this debate, and I still don't believe that data is going to solve the problem of robotics. So with that in mind, so my question is, and let me just give you an analogy here. All of us were born with brains not bigger than the size of an orange, and yet we have been able to understand the physical world around us. We do not require the processing power of an Empire State Building set on its side in order for each one of us to learn. So there is something fundamentally wrong with the thesis that throwing more data at the problem is going to solve the problem. So, and then the last example there, again, bringing the analogy back to human brains, which is what I did my PhD thesis on way back when, is essentially, look, you do not remember in your brains all of the data that you processed to create the models that you are carrying with you for the rest of your life, right? Because what was valuable to keep was the model and not the data. So with that, I just open up the question to the data side of the team.
All right, great, okay. Good. Actually, thank you. And I'm going to let you respond. And then I think just because you guys are persisting, staying there, you guys are the last few. But just we're going to take the last 4 questions all quickly, and then we're going to turn it back to the panel. Okay, great. Thank you.
So, of course, the data is used to build something. We are talking about data-driven modeling of the world. And so the data by itself, of course, is interesting. But what we are doing in robotics, in data-driven robotics, is to learn from the data, to look at the data. And through the models, we can learn general principles. We can learn solutions. We can learn policies. We can learn not just how to move from point A to point B. We learn an entire policy where we can generate a range of paths. We learn the kind of the abstractions of what is essential to move from point A to point B, rather than the specific pixels and the XYZ coordinates that we would get from a purely physics-driven algorithmic solution.
Okay, good. So again, we're going to take these questions. Just say your question really quickly if you can, without preambles.
Okay.
Go ahead.
So I want to build robots to find and identify never before seen life, either in space or the deep ocean, and deploy it. Which method do you think gives you the best chance of doing this, especially if it's only been trained on things that it's seen and it's guaranteed to be something extremely out of sample?
Okay, wait, what was the problem again?
I want to find and identify new life, either in the deep ocean or the deep space.
Oh, okay. Wait,
so
you're,
which method gives me
you're
the
moving
chance?
into another question. All right. All right, thank you. We'll take that into consideration. Yes, go ahead. Go ahead. Yeah, okay, the question was what will be necessary to discover life, other forms of life, either deep in the ocean or in outer space. Okay, so go ahead.
What underutilized data streams or sensory modalities we have not exploited yet for robotics? An example could be that in LLMs we discovered that human preferences could significantly improve the models through RLF.
Okay, good. What other data streams have we not discovered yet? Very good. Excellent. Next question?
Okay. Thank you. So, to the data team, how much data do we really need for us to trust the robot's operation? Like at a probability of success high enough? To the model team, how large of a model do we need to for the robots to complete very complex tasks? And when they are large enough, do they become something that we all know as something else?
Ah, interesting. Okay, good. How much data do we need to get high reliability, sufficient reliability to trust them?
Okay,
Yes.
I have a quick question. So for autonomous vehicles, you can collect data on the road and it's all like public free. But when you're building a humanoid robotics, how do you make sure that 8 billion of people in this world are happy to share the data with you? So how do you collect all this data that's related to human? Because everyone cares about the privacy. So yeah, thank you.
Oh, good. Privacy question has come up. Okay, good. Thank you.
So pro data guys, this is for you. So we all know attention is all you need, okay? So at this point, I feel they are good for chopping apples, but not for making dishes. For long horizon tasks, I would like to say cognitive models are all you need. If you want trust, how do you defend yourself in this case?
Okay, good. I'm not sure I understood that completely, but but okay, great. So let's move on to the last stage. Okay, so I'm going to let everybody give a chance to say a 1-minute wrap up. Anything you'd like to share, or you can pass. But Daniela will give you the honors first.
If we want robots to operate in the physical world among us, we have to be able to get those robots to perform complex tasks. And there's no way to model those complex tasks from first principles. No algorithm will create a solution that will be adaptive and generalizable and deployable in a wide range of environments. We need data in order to learn policies, in order to learn the essence of what it takes for a robot to execute a task.
Thank you. Okay, great. Aud will be next, and then it comes to Animesh.
Okay, to the question on the complexity of the model, we often think those days that the more complex the task, whatever we mean by complexity, the more data we need. So if I go back again to the analogy with cosmology, it wasn't that we got more data, it was that we got finer data that allowed us to develop more complex models. So it's not the quantity that matters, it's the differential. It's new data that gives you new information, and then you can build a more complex model based on this new information.
I think we are in an era where we have to do a lot of empirical work before we can do science again. Trying to compare current intelligence or robots with any sort of efficient biological systems is like saying, oh, the plane you got here was less efficient than the bird, or you run faster and more efficiently perhaps than a car, yet we do this. So we need systems that actually work first before, and then we can talk about ideas of efficiency, compression, and all sorts of stuff later. Talking about efficiency right now is just analysis paralysis.
Right. I think we all need to have better experimental methodology, and we need to define the problem we care about and really define distributions over problems for robots to solve, and really test multiple strategies fairly and carefully head to head. And I don't think any of us are very good about doing that. We often show our best results. We often pick the problem to suit our methods. And I think the question of how much data do you need, how big a model do you need, and so on, those things will come out if we do collectively our experimental work better.
If you want to solve robotics, sincerely, if you personally want to solve robotics, whatever that means to you personally, you have to be willing to revisit and revise your core beliefs. You have to be willing to possibly throw out the things you know and love, and be willing to admit that there's something new and exciting happening. Everything you've learned, all the deep thinking you've done, you can bring that to bear and look at these new problems differently. But I think we have to admit that the world changed. There's a new kid on the block, and we need all of your brains to raise your hand on the right side of the equation and just start studying this thing.
I completely agree with Russ, and I think all of you do too. I think, you know, learning is here to stay. We all want to use it, but we want to do it the right way. And you know, CNNs are good for something. Transformers are good for something. Why are we using CNNs and transformers for robotics? You know, Daniela talked about state-space models. You can actually do better. You know, there are things like feed-forward and feedback terms, and we're all so fixated on policies. So we have to really, you may have thrown out your old vision books. Don't throw out your physics and robotics books yet, because there's a lot of good stuff in there that you can use to build foundation models the right way.
All right. Okay. Very good. Thank you, guys. You're amazing. So how many now believe that data will solve robotics? Hands up. Ooh, there's definitely an increase here. All right. Okay, Russ, you guys, Animesh, Daniela have done some good work. How many believe that it will not solve robotics? Okay, there's still some. All right. But I do think there was a little bit of a change factor there, I noticed, and I call it good old-fashioned engineering. I think there's still room for it. It's going to be around. Don't throw out your handbooks of robotics, and let's continue this debate over some drinks. Thank you, everyone.